Okay, let's take a look at a little more. We have problem 31 on page 192. You're going to be doing one like this as well. And the directions, we need to find the function with the given derivative whose graph passes through the point P. So what we're in effect finding is the antiderivative. So I'm going to first rewrite this like in this format, because now what I want to do is think about going backwards. So to find the antiderivative, I'm going to increase the power by 1. So if I add 1 to this, I get x to the minus 1, still a negative sign there, and I'm going to divide by my new power, or it's multiplied by the reciprocal of the new power, which is the same as dividing by the new power. So I end up with just x to the minus 1. And you can verify that. Negative 1 times x to the minus 2 would be the derivative. But don't forget, this is plus a constant. We don't know what that constant is. However, we know that it passes through the point 2, 1. So the value of the function is 1, so that's going to go in on this side, when x is 2. So this would be 1/2 when I plug in a 2. So I get that c equals 1/2. By the way, this is 1 over x plus c. So then I get that my function f of x equals to 1, equal 1 over x plus 1/2. And I still have this domain value that they gave me before, x greater than 0. I think the reason for that is when x equals 0, the function would be undefined, so would the derivative. So they just avoided that by just giving you a portion of it where the function is defined for all the values. Okay, I want to take a look at number 36. On number 36, we're asked to sketch a graph of a function f of x, and we're given some particular information. So we're told that f of 2 equals 3, and we're told that f prime of 2 equals 0. And then we're given some various information, and we need to sketch a graph for each type of problem. So first we're told that the derivative is positive for x less than 2, and we're also told that the derivative is negative for x greater than 2. Now we have a lot of information here. Remember when the derivative is positive, what does that mean about my function? That means f of x is increasing. And when the derivative is negative, remember this tells me that f of x is decreasing. And we have some information from this up here too. If my derivative equals 0 when x equals 2, then x equals 2 is a critical point. Okay, so we have all that information that will help us draw our graph. So if I go ahead and draw this, and I'm going to count by ones. So I'm told that f of 2 equals 3, so I know that I have this point. It has to go through this point here. I know that my function is increasing up into that point, and then after that it is decreasing, and it changes directions there. So I could have something like this. And it could be continuing to go down there, having some problems there with the pin. That's a possible graph, and that's what the directions say, to sketch a graph that has those properties. So there would be other graphs that could have those properties, but that is a possible graph. I'm going to skip part B. If you look at that, you can see, I'm sure, that it's just going to be reversed. So I'm going to go to part C that says f prime of x is less than 0 when x is not equal to 2. Okay, so again, this is telling me that my function is decreasing, so f of x is decreasing. All right, when x is not equal to 2. So if I were to sketch a possible graph for that, still with my same criteria from before, so we still have f of 2 equals 3, so that's still true. And now my function is always decreasing. So it's got to be decreasing, but remember, we have a critical point there. So I can't just draw a straight line. What I could do, though, is something that looks like this. It's decreasing, it's still decreasing, but I have some kind of function that may look something like that, where so f prime of 2 is still going to be 0, and but my function is always decreasing. So that would be a possible sketch for f of x. Okay, I'm going to take a look at one more problem, problem 41 in your textbook, and you're going to need to turn to that on page 192. I'll read through it, even though I don't know how to pronounce this name of it. Classical accounts tell us that 170 or trireme, I'm not quite sure, but it's an ancient Greek or Roman warship, once covered 184 sea miles in 24 hours. Explain why, at some point during this feat, the warship speed exceeded 7.5 knots, which is sea miles per hour. So we're told that it traveled 184 sea miles in 24 hours. So if we were to take a look at the average speed over that 24, if you take 184 sea miles, divide by 24 hours, you get an average of 7.667 or 7 2/3 sea miles per hour, which we're also told is knots. Now, since remember that the mean value theorem says that if it's a closed interval, which it is, and it is differentiable function, which this would be, then the average, at some point, the average speed has to match the instantaneous speed has to match the average speed. So that would mean that at some point it had to be going at least this fast, 7.7 2/3, which is greater than 7.5. So because of the mean value theorem, we are guaranteed that at least once it would have had to have been going more than 7.5 knots. So that's using the mean value theorem is how you could explain that. Okay, I think that's going to be it for our examples. So you will need to be working on your homework from section 4.2.